This is the GT Campus Traffic and Transit Analysis by Peter Durham
and Luke Raymond. So the reason we chose this topic was because we want to understand traffic dynamics around us on Georgia Tech's campus. We also want to understand bus service gaps and analyze how Stinger transit coverage differs between different routes and first weekday and weekends. And we want to identify congestion patterns while also improving student transit decisions.
Our initial hypothesis for historical road congestions, we think interstate roads near Georgia Tech will carry more daily traffic and truckload than other urban roads around Georgia Tech. For the transit service gaps, we think the weekend Stinger service will be a lot slower compared to weekdays due to fewer routes and longer wait times between buses. The live traffic conditions, we think the real-time speed and jam factor data can be used to classify congestion levels on roads around Georgia Tech campus.
So onto the data sources. I found these because I wanted to do something relevant to Georgia Tech and traffic around Atlanta, which pertains to a lot of people that come here. So that's how I looked up the Georgia Tech Stinger routes, and then I decided I want to look at historical traffic patterns, leading me to find the downloaded CSV file with traffic counts across Georgia. And what's cooler than having live data that can change every second? So that's how I ended up going to this live API, which shows real-time traffic patterns around Georgia, and I can limit that to within ATL as well. To clean the CSV style, we started by removing a redundant column, and then we looked into Georgia Tech's main campus by creating a geographical boundary around it and limiting ourselves to road segments within these boundaries. And then we looked into handling inconsistency, where we replaced missing data with the average of other values within that same row so that we weren't replacing with values with skewed averages from other road segments. Next, we deleted some irrelevant rows, and then looked into handling another inconsistency, where we combined rows with duplicate station IDs by condensing them into one row. And then I created a data summary columns so that I'd be looking at the data that I wanted to put into my final data frame. And finally, for the last consistency that we handled in this data set, we replaced missing average truck percentages with the mean average truck percentage from the same functional class. And then we outputted this to a new file and created a new data frame. Next, we look at the web requirement, where we looked at GT's transit website. And first of all, we started with retrieving the data from this website, and then extracting data from the table. And then next, I standardized the route frequency, where rather than having 20 non-peak and 30 peak, we decided to just call it 25 for future calculation purposes. And then we handled inconsistency, where I removed unnecessary characters and converted it to integer data type so that I can do calculations within the future if needed. And then I converted the times to pandas format so that I could calculate the duration. And then I outputted this to a new data frame and new output file. And this slide is the exact same as the last slide, but this function focuses on the weekend table, while the last one focused on the weekday table. So they output the same thing, but one is for weekdays and one is for weekends.
Here's our live traffic API. First, we define our boundaries using the same bounds as our CSV file. We then get our API data within these bounds. We extract our data and handle an inconsistency in street names. We then change the speed units and add in our column headers. We create our data frame. We fix invalid street name issue. We remove exit from street names, and we split the streets into two rows if they are joined. So after that, we standardize highways and directions. And then we remove any blank street names and handle missing and unreliable data. Then we find streets with the same name and average out values to have more accurate data. Then we change the jam tendency to a description so users can better understand what's going on. We then round our data values and output our file. Our first insight is the linear regression model that we use to predict actual road speed against free flow speed. This insight revolves around live data, so the key metrics may change each time it runs. For every 1 mile per hour increase in a road's design speed, the actual transit speed increases by 1.02 miles per hour. Here's our visual for the linear regression model. So on our x-axis, we have the free flow speed, which is our expected speed without any traffic. And on the y-axis, we have the current speed. So this trend line of y equals 1.02x minus 4.94 means the actual speed is predicted to increase by 1.02 miles per hour for every 1 mile an hour increase in free flow speed. So this gray line is a baseline where there is no traffic, no congestion. And so we see that the roads run slower than their free flow speed and high speed and low speeds. However, most speeds near GT campus are low speed urban streets. In Insight 2, we break down the road by functional class. We use this to compare the average traffic count and the truck percentage and impacts. In our findings, we find that the interstate road class has the most amount of traffic with only 4.05% trucks. We also find urban local roads have the highest truck percentage. However, it has low overall traffic volume.
So Insight 3 focuses on bus route service gaps. This portion of the code focuses on comparing GT Stinger bus service between weekdays and weekends by total trips, average frequency, and total operating hours. We see that weekdays have way more trips, shorter frequency, and higher total service hours compared to weekends. So this is part 2 of Insight 3, which focuses on comparing specific bus routes within the weekend domain and specific bus routes within the weekday domain to each other within their separate fields. For example, you can see that on weekdays, Cloud Route runs the most frequent at every 14 minutes, and Blue Route and Red Route tie for the longest runtime at 52.5 total hours. And then you can also see another metric on weekends, where the Blue Route, Gold Route, Cloud Route, and Red Route tie for longest runtime at 8.25 hours. Visual 3 goes along with Insight 3, where you can see the overall weekday service volume compared to weekend service volume. And you can also see the individual bus routes compared to each other within their own sector of weekday and weekend. You can see which routes have the least total trips and the most total trips within their domain. You can also see that overall weekday has way more total trips than weekend. So Insight 4 is a real-time congestion snapshot. First, we classify each jam factor value according to its threshold, where we call it free-flowing, moderate, or heavy. And this framework of classification can be used to further identify which heavily congested roads are actively getting worse, which ones are getting better, and which ones are stabilizing. So this provides us with real-time insights onto what is going on with the congestion levels around Georgia Tech's campus. Here's a real-time visual from the first part of Insight 4, and the visual updates with real-time, and right now you can see the different classifications of the congestion levels, with 48.7% free-flowing, about 40% moderate, and about 10% heavy. For Insight 5, I use a K-nearest neighbors classification to predict whether a road near GT is free-flowing, moderate, or heavy congestion level based on its current speed, free-flow speed, and confidence score. To find the best K-value, I look for the K-value with the highest accuracy, which I code into the insight so that each time the live data is ran, I can find the best K-value. The high accuracy and weighted F1 score together confirm that congestion level can be reliably inferred from raw speed data alone without needing a pre-calculated jam factor.
Here are some challenges and learning experience from this project. We learned how to use coordinates to find streets around GT campus to bound our data by. We also learned a few new methods and parameters. We had to do some critical thinking to solve missing values and other cleaning issues. And we learned how to adapt our visualizations to portray our insights. We built helper functions to classify and label data into readable, meaningful categories. and we also had to keep improving our cleaning process by looking at our output files. Thank you.